When a massive commercial ship leaves a river and enters the ocean, it literally rises out of the water. Archimedes' principle states that a floating object will always displace a mass of water exactly equal to its own total mass. This gives us the core equation of vessel hydrostatics. Displacement, which is the total mass, equals the immersed volume multiplied by the density of the water. During a typical voyage, a ship's total mass stays constant. But as the vessel moves from a freshwater port into the open ocean, the density of the water changes, unbalancing the equation. To maintain that fixed mass, the volume of displaced water must shift in the opposite direction. Physically, this means the ship's draft, how deep it sets below the waterline, has to change. We need to build the exact mathematical framework naval architects and deck officers use to calculate these density-driven draft changes. Miscalculating this relationship carries massive consequences. You either leave tons of profitable cargo on the dock, or you overload the vessel, risk sinking, and violate international safety laws. To isolate the variables, we start with the simplest conceptual model, a perfect box-shaped vessel. First, we lock the vessel's displacement. The total mass is constant, representing a ship in transit making no cargo transfers. This diagram compares our box in freshwater at 1,000 kilograms per cubic meter and saltwater at 1,025. Because saltwater is denser, providing more buoyancy, the box requires less immersed volume to support the same mass. Immersed volume is simply the length of the vessel multiplied by its breadth and then multiplied by its draft. For a rigid rectangular box, the length and breadth cannot change. Therefore, the draft is the only physical dimension capable of shrinking to reduce that volume. If the density of the water increases, the ship's draft must definitively decrease. This gives us a formal geometric ratio. The new draft divided by the old draft equals the old water density divided by the new water density. For simple geometries, the change in draft is a pure inverse ratio to the change in density. We can predict exactly how far the vessel will sink or rise without complex calculus. Next, we flip the constraint. Instead of locking the mass, the ship must now maintain a constant draft, perhaps to clear a port's shallow depth restriction. By locking the draft, we completely lock the vessel's immersed volume. Here, the models show the box maintaining an identical draft depth in both freshwater and saltwater. When this exact same volume is submerged in denser saltwater, it generates a significantly greater upward buoyant force. To counteract that extra buoyancy and force the ship to stay down at that constant draft line, you must increase the ship's total displacement by loading more weight. The math here is a direct proportion. The new displacement divided by the old displacement equals the new density divided by the old density. Denser water equates directly to higher cargo capacity for a fixed draft. Calculating this difference is a critical financial lever for shipping operations. In reality, commercial ships are not rectangular boxes. A ship's hull is curved, tapering at the bow and stern. As the draft changes, the cross-sectional area of the hull intersecting the waterline changes continuously. Because of this curve, immersed volume does not scale linearly with draft changes. To bypass this complex 3D hull calculus, naval architects use an empirical workaround called the freshwater allowance. Freshwater allowance, or FWA, is the exact number of millimeters the mean draft changes when a ship passes between pure saltwater and pure freshwater. To find a specific ship's FWA, you divide the total displacement in tons by 4 times the TPC. TPC stands for tons per centimeter. It is the exact mass required to sink the vessel by 1 centimeter at its current draft. This math is physically stamped onto the side of every commercial vessel as the statutory load line disk, also known as the plimsoll mark. On the grid, you'll see a mark labeled S for summer salt water, and above it, a line marked F for freshwater. The perpendicular distance between these two specific marks is exactly equal to the ship's calculated freshwater allowance in millimeters. FWA converts complex 3D non-lineal hull geometry into a simple lineal measurement stamped directly on the steel hull for instant use by the crew. Commercial ships rarely load cargo in pure fresh water at 1,000 kilograms per cubic meter or pure open ocean saltwater at 1025. Most global ports and berths exist in brackish dock water, which features intermediate and constantly shifting densities. To calculate draft changes in these intermediate zones, officers use a metric called dock water allowance, or DWA. Dock water allowance calculates the exact change by multiplying the FWA by the difference between the old density and the new density, and then dividing by 25. DWA simply scales the known freshwater allowance based on a ratio of how far the actual dock water density is from pure saltwater. The denominator, 25, represents the absolute density spread between standard freshwater and standard saltwater. DWA provides the exact millimeter allowance an officer can legally submerge the vessel past the saltwater summer mark while loading in a brackish port. We now have a complete hydrostatic framework for density effects. This flowchart represents the unified decision tree for these scenarios. If displacement is locked, officers use density ratios, FWA and DWA, to predict the changing draft. If the draft limit is locked, they use density ratios to calculate the new maximum cargo allowed. Choosing the correct pathway governs the entire cargo loading strategy and safety profile of the voyage. This math is what allows a vessel to optimize its payload capacity before casting off. By mastering these variables, a deck officer ensures the ship extracts maximum financial value by loading deep in brackish ports, armed with mathematical certainty that it will safely rise to its legal load line in the open ocean.